In this video, I'd like to just review a couple questions that I saw while working on some of the Math Excel for these last 2 weeks. These are methods that we use to calculate the volume of an object using the general slicing method, not slicing by disk or washer or shell, but slicing in general. So one of the problems that I saw was talking about this semicircular shape where it's the top half of a circle. And just a reminder, the equation of a circle, a full circle, would be x squared plus y squared equals 12 squared. Now that's not a function, but if we were to isolate y, and we do that by subtracting x squared over and then taking a square root, we'd end up with the equation 12 squared minus x squared inside of a radical. Now, in the act of doing so, if I retain both the positive and negative copy of the radical, then we would have the full circle described visually. If we retain only the positive square root, or the primary radical in this case, then we have just the top half of this section, and life is good. Now, in three-dimensional rendering, if we show a triad of axes here, we usually put x, positive x towards the front, like coming at us off the page, positive y to the right on this perpendicular axis that we can see, and then the z-axis being the three-dimensional space, positive going up like that. So if I were to sketch this, I'll use, 2 grid lines per, 2 units per grid line, so 2, 6, 8, 10, 12, this semicircle in this orientation, so towards the y-axis, perpendicular, if you will, to the x-axis. It's going to end up looking something like this. Our semicircle lives out in this region. Now, I'm not being hypercritical on the sketch here, but hopefully you can see in this orthogonal view that this is a semicircle laying down in the xy plane. Now, that word problem goes on to state that what we're looking for is the volume of the three-dimensional shape created like this, where we generate squares that are perpendicular to the plane where the semicircle lives, and we use the semicircle as a boundary, if you will, to these shapes. So it's kind of tough to draw, but hopefully you can kind of see what's happening here. As we slide further to the positive y values, we end up generating all of these smaller and smaller squares. And again, we're using the edges of this semicircle to limit the shape here. And I don't know how you would describe this particular shape, but you can kind of see what's happening here. So what's important to kind of notice is, I recommend thinking about the geometry necessary to calculate the cross-sectional area of each of your slices. And we're dealing with squares here. So in my mind, I'm thinking, well, the area of a square, that's easy. That's side length squared. But then now you just have to be careful and think about how you want to set up your integral to accomplish this task. Each of these areas is effectively the length along our x-axis twice. So if we have a length to the positive x-axis, that's this section right here. And then the length to the left side, that's a negative x quantity. So if we wanted to build the area of the red square based on x instead of just some arbitrary side length, then the side length, since the side length is 2 of these lengths of x, we could say that the area is 2x squared. And so if we commit to that, then we ought to be able to build a volume function based on x, and that would be the integral for x boundaries from negative 12 to positive 12, because we're now talking about boundaries from negative 12 to positive 12 on the x-axis, where the height of the, or I should say the dimensions of the square, end up being that 2x for the side length squared with respect to x. But the problem that we have with this particular equation is that the formula that we've given here, in a sense, it gives us a nice cross-sectional area of this rectangle, but it doesn't provide any sort of boundary in this direction. It doesn't provide any sort of indication that we have this semicircular cap or semicircular base that we're working towards. This function doesn't describe that whatsoever. In fact, I believe if we compute this volume, it may not generate a cube for us, but something similar to that. We'd have to sit and maybe think about it some more. But this shape, being linear as it is, maybe it'll generate a pyramid of sorts. I don't know. I have to sit and think about it just a little bit more. It's not coming to me right now. But we're really close. In order to account for this semicircular boundary, we can come right back to the equation that we were using to describe that semicircular boundary. Now, we have a function that works pretty well in terms of x. We want to integrate in terms of x, and 2x will represent the radius in this direction of that semicircle. But if we come back to this definition and rearrange it just slightly differently, instead of saying that y is equal to the positive square root of 12 squared minus x squared, what if we go with this version? X is equal to the square root of 12 squared minus y squared. My color scheming is about to get a little bit wild here. If I only retain the positive component of the radical, then we're really only talking about this region of the semicircle. So this portion here, it stops at the x-axis. We're not accounting for any negative x values at all, but that's okay because due to symmetry, we have this region, this positive semicircle, and to be clear too, it probably should be included this far. This semicircle, and due to symmetry, it would be reflected and repeated in the negative x region. But number one, I'm not interested over here, and we can limit that with our boundaries of integration when it comes to setting up our integral in just a second. And secondly, I'm going to take advantage of the symmetry because we've already kind of accounted for it over here already. We know that whatever the x value is, we're going to double it to obtain the amount of area that exists in the negative x region. So see if you can stick with me for just a minute longer. If we draw the volume formula based on y instead of x, and I'll be real deliberate here, volume based on a y coordinate, then that means our boundaries of integration have to exist on the y-axis. So now we're starting from a y value along the x-axis, so that's a y value of 0. We're going to go up to a y value of 12, so we'll use 0 to 12 on our boundaries of integration. And we'll use 2 times x squared. Well, we just said that x is equal to the function in terms of y, 12 squared minus y squared under a radical there. With respect to y, we'll integrate with respect to y. And then from here, we can do a bit of algebra to clean things up and simplify it. Or, to be perfectly honest, we might just go to our calculator and compute the result. And we can get an answer for the volume that way. Now, with this other example, we have a description where we've got a triangular base at the coordinates 0, 0, at 4, 0, so that's 4 on the x-axis with 0 on the y-axis, and then 0, 4, so 0 on the x-axis, but 4 on the y-axis. That would be here, again, if we're adopting the x, y, z right-hand coordinate system. So I have this triangle that's acting as the base in three-dimensional space. And the cross-sections of the three-dimensional object that we're looking at are semicircles that are perpendicular to the base but parallel to the y-axis. So in the direction of the y-axis, so going this way, perpendicular meaning 90 degrees to the face or the base of the shape here. So we're talking about semicircles that are oriented like this. And I think in class a couple weeks ago, when we were actually introducing this, I started calling this the slug pattern. Because this almost, if you think about all of these concentric semicircles here, it almost kind of looks like a bit of a slug. We've got the top half of a circle laying in the shape of a triangle. Now, I think what helps here is recognizing this line, this boundary line right here that goes between 0, 4 and 4, 0 on the x and y axes. If I turn to a traditional Cartesian 2D coordinate system, that's this shape in this orientation, so 0, 4, and 4, 0. The equation that goes through this is the equation negative x plus 4. So we have a slope of negative 1 with a y-intercept of 4. And we would use this equation on x values that exist between 0 and 4. And that's what would limit our shape to this little region right here. So if we take that into consideration and now recognize the cross-sectional area of each of these slices, well, that's a semicircle. So a circle itself is pi times radius squared. If we want a semicircle, we'll just take half of it. So half of pi times radius squared. And if we look a little bit more closely on this shape, the radius of this semicircle ends up being half of this length of red. Well, this length in red is our y-coordinate, so we could think of the area as, I'm just going to write it this way, 1/2 of pi times radius squared. Well, the radius is y, so I'll say half of y squared. And then on top of all of that, we're noting that y is the result of this equation. So the y-coordinate along the way ends up being the result of this negative x plus 4 equation. And that's going to be particularly helpful because we've already discussed how we only want to use this equation on a boundary of x. So area would be 1/2 of pi times 1/2 of negative x plus 4 quantity squared. And now I can introduce this as an integral with boundaries on the x-axis and integrate with respect to x. So the volume ends up being the integral from an x value of 0 to 4 on the function 1/2 pi times 1/2 of negative x plus 4 quantity squared. And again, integrate with respect to x. Now this is something that we could bring to the calculator if we're just looking for a solution. We can spend some time using algebra to isolate all of this if we wanted to as well, and that would be just fine. But I think this formula does a really nice job for us. It captures the cross-sectional area, so half of pi times some radius squared. That gives us the area of a half circle, of a semicircle. The radius in and of itself is half of the y-coordinate. So here's a radius, here's a radius, here's a radius. These are all radii for the circles that are going to go in this direction. And this little mini function right here is what's giving us the height or the dimensions of those circles. So it's all built in there. So interestingly, for just one more minute, if you'll indulge me here, if we had a similar shape, but it wasn't a straight line edge, maybe it was a little bit more wavy or something like that, we could do effectively the same thing. We now have this kind of a blobbish looking slug, if you will. That can be accounted for with simply a new equation right here that describes the boundary line that we're facing in this region too. So some small tweaks can change the volume and compute the volume and for a different shape. And I think that's pretty neat. That's kind of a neat little trick that we can employ with our slicing method in calculus. So hopefully those two examples help you out just a little bit with a general slicing method. Again, please feel free to message me through Math Excel or by email, and I'll do my best to answer those questions one-on-one. You can, of course, see me before school and after school for extra help as well. Thanks.